The first part we're going to bring up is water. It's a super simple liquid. You could argue it's not even biophysics, but it's the basis of all this interaction with biophysics, and that's why we need to start there. This is a computer simulation of water. I figured it's fun to start that way because you've all seen experimental water, I hope. In terms of water here, this is probably 10 picoseconds or so it's very much physical timescales, hardly chemistry. But this manages to reproduce all the properties of water. The diffusion coefficient is right, the heat of vaporization is right, the boiling and freezing points are going to be right. And you even get some properties such as solubility of a piece of oil or something roughly right. The other thing that you might see here is that although this is liquid, the molecules can move around. It's kind of like a mesh network. So all these molecules interact quite strongly through hydrogen bonds. These hydrogen bonds, if we had a perfect ice crystal, every single water molecule would have an average 2 hydrogen bonds formed per molecule. It's slightly less in water because it keeps breaking a few of them, but it's actually as much as 1.7 around room temperature. So most hydrogen bonds remain formed even when water is liquid. And that's what gives us very special properties, in particular a very high boiling temperature and a very high melting temperature. Most other simple liquids that you know about, you probably don't even think of them as liquid, but oxygen can be a liquid, methane can be a liquid, carbon dioxide can be a liquid, and even most noble gases can be liquids if the temperatures are low enough, and low enough in some places might mean 0.1 Kelvin. The reason why you need to go to so low temperatures is that those molecules don't really attract each other very strongly, so they prefer to be gases. Water, on the other hand, due to these hydrogen bonds, the molecules will attract each other very strongly, and due to this attraction, that means that they're going to form something called condensed phases, where atoms prefer to be together rather than more or less infinitely far away. And that's the whole definition of a liquid or solid. In water in particular, these hydrogen bonds have strength in the ballpark of, say, 2 kilocalories per mole. We're going to come back to those energy units later on, but it's important to be aware that whether it's kcals or kilojoules or kcals per mole, you can use absolutely anything you want, but you need to get it right. It matters that this is per mole. The actual energy of an interaction between two waters is almost nothing. And that's why we're having it per Avogadro's number of molecules here to get easier numbers to talk about. Inside proteins, there are also hydrogen bonds. The strength there varies a bit more. Some of them are very weak, but some of them can be a bit stronger because those molecules are more polar. So maybe up to 5 kcals per mole or so. The reason why we get those hydrogen bonds, despite each water molecule is neutral, it's not like an ion. But inside this water molecule, the oxygen here is a very electronegative compound. So it's going to steal some of the electrons sitting on the hydrogens to create an excess electron density around the oxygen here. And it's so much that it's almost as if we had a full extra electron on the oxygen. Now, it's not an extra electron. It's stealing those electrons from the hydrogen. So that corresponds to taking half that charge from each hydrogen. So the hydrogen is then going to have an excess plus charge. That means that this molecule is effectively going to be a dipole. So this dipole then means that it's like having a small arrow pointing from the red one, that's negative, towards the center of the hydrogens. That would be the effective positive charge here. One such molecule doesn't make a ton of difference, but if we now take many such molecules, this positively charged hydrogen would suddenly love to start to interact electrostatically with this negatively charged oxygen. And then we're effectively creating an electrostatic interaction here between two different molecules. And that's, given the magnitudes of these numbers, this is going to be quite strong. So strong that it's not quite a covalent bond, but almost. And that's why they remain formed even when we have the water in liquid and the molecules are moving around. This dipole property of each water molecule is also what gives us some of the properties that you might have seen, that if you take a comb and charge it, for instance, by just combing your hair or the skin of a cat, that means that we have a negative charge on the comb, electrons in that case, and that we can use that to push away atoms so that this negative charge on the oxygen is going to repel the electrons on the comb.